Welcome back. Our second talk this afternoon is going to be by Nicolai Reshetikhin from the Yao Math Sciences Center at Tsinghua University and DIMSA. He will be my former colleague at Berkeley, I should mention. And he will be talking on invariants of tangles with a flat connection in the complement. Thank you.
Next, reduced by formal calculators.
So, can you use this as a pointer?
Yeah, and also move the slides.
Well, the thing is that
You mean if you click
I don't know, pointer we cannot really see.
It's true.
Yeah, this is the pointer. It's not how.
Can't see the pointer, but that's because
I
you
tried
to
very much. I cannot see it.
I can see it.
You cannot see it. Okay. Then I have a strong pointer. So, so this will be. So in 2006, with Kashaev, we wrote a paper on this subject. And we constructed, using representation theory of quantum groups at the root of unity, these invariants. So these are invariants of tangles, in particular invariants of knots with a flat connection in the complement. So you can think of these invariants either as invariants of pairs, or not in a flat connection, or tangle in a flat connection. Or you can think of this as, well, it's probably the best way to think about it. So, I promised Maxim, he is not here, that I'll make a decent joke about him. But I thought, instead of a joke, I'll just say, I know him for many years, and I learned one thing. If he gives a talk and it seems like it's some kind of strange thing, then one should really take it seriously. I don't know any strange talk that he gave that wouldn't lead to anything, to something interesting. So I remember he gave lectures in Berkeley when he was there for 1 year about deformation quantization. I think nobody understood anything. But then, when I was reading his paper, then all became clear. So now the plan is the following. I'll just so first of all, this talk has nothing to do with mirror symmetry. And so I'm really grateful for the organizers that I'm invited to the mirror symmetry conference, but it has nothing to do with mirror symmetry. So first I will remind this notion of tangles and the diagrams. Then I'll say a few words about flat connections in the complement to a tangle. So then I'll give I'll remind Wirtinger presentation, combinatorial presentation for representations of pi1 into G, and then I'll give a local description of this combinatorial data that we derived with Kashaev back in the days. So something that we didn't pay attention to, absolutely, but something that always existed in the picture is the Poisson structure on the center of the quantum group at the root of unity. So I was a little bit puzzled why we never used it and where it fits. And basically in this talk I will explain where it fits and how it naturally appears in geometry of Poisson. So then the main motivation is really topological quantum field theory. So there are many versions now, and I think Grom-Fitton theory is one of the examples of TQFT. So, but if you go back to the story about quantum Chern-Simons, there is some unresolved problem. So there is a combinatorial description that's due to Turaev and myself, and there is a geometric vision of this theory by Whitman. And everybody believes that it's the same thing, including myself, but it's not the same thing. If you write the path integral in some kind of reasonable sense, the most reasonable sense is the asymptotical expansion. So the kind of way to check this kind of old conjecture is to take the combinatorial invariant and consider the asymptotical expansion when the level goes to infinity. So then conjecturally you will have the sum over, say, SUN flat connections, and then from each flat connection you have perturbative contributions. So there is this dichotomy between geometry and algebra. So here in what I will be talking now, this dichotomy is built in. So the invariants, they have this quantum parameter, non-perturbative quantum parameter, and they have flat connections. And then I'll explain what one should expect from them. Okay, so the tangles, this is a picture of the tangle. So we consider framed tangles and oriented, and it's something that's hanging between two planes, and on each plane one should choose a line. There are many reasons why the endpoints of a tangle should be on a fixed line. One of them is that if you want to derive this picture geometrically from solutions to Newton's homological equation, then we have to eliminate monodromies, and that's why the boundary points should be on some line or on some curve. Okay, so this is kind of a formal reminder of the tangle. So a geometric tangle is smooth embedding of intervals and circles into the cylinder R2 cross identities such that the endpoints of intervals, they belong to these lines on the boundary surfaces. So lines are in R2 fixed. So then frame geometric tangle is a tangle with the continuous section of a normal bundle. So these little arrows there, this represent this section. And the endpoints, the typical arrangement is that the frame is perpendicular to the line L. So that's so-called blackboard frame. Now, topological frame tangle is the regular isotopy class of a geometric tangle. So to such that the boundary is constrained to L. So by regular isotopy class, I mean on the boundary, these points can be continuously deformed, but they cannot collide. Okay, so then we can project the tangle to the line to this green plate to here. So that's the projection. And the result of the projection is of a geometric tangle. Again, it's a geometric diagram with only double point singularity, so we can always continuously deform the tangle so that there will be no other singularities. It should be transversal to these lines at the boundary. And topological diagrams, these are regular isotopy classes of geometric diagrams, but these are regular isotopy classes on a plane. So diagrams form a rigid monoidal category. Objects are plus minuses. These are the identity morphisms. The morphisms are diagrams. so pluses and minuses indicate where the diagram is oriented at the boundary. Composition is just gluing. Tensor product is juxtaposition of objects and of morphisms. This is some standard 40 years old, 30 years old stuff. So, then the dual object is you change the order and reverse the signs, and then it accompanied the dual object by the evaluation morphism and injection morphism. So all this together is braided, sorry, not braided, just monoidal rigid category. It's not braided. So then framed tangles, they form a rigid monoidal braided category. The braiding is on the picture, and then there is this theorem by the Meister. So it's here it's the version for tangles. So it's a framed version of the Rademeister's theorem that if you take diagrams are isotopy classes on a plane, modulo Rademeister moves. These are the moves where singularities we change singularities. So then this category is naturally equivalent to the category of tangles. So in other words, it's very convenient to think about tangles as Rademeister equivalence classes of diagrams. So, and this is a way how we will think about it. But then there is a natural question. So suppose that you have a flat connection in the complement to a tangle. So you choose a base point, and then it gives you a representation of pi1 with this base point, because you can take the holonomy for the flat connection around various parts of the tangle. So the question is, how combinatorially describe these representations of pi1? So the answer is no. Wirtinger gave the answer for knots, for links. It's very easy to modify it for tangles. So first we want to describe the representation space by 1 to G. So the description is the following. We take a diagram of a tangle, and we're describing the representation of pi1 of the complement to a tangle in terms of some decorations of a diagram by elements of our group G. So then this is the Wirtinger description. So we color the edges of a diagram by the group elements like this. And that describes representation of pi1. And the idea is the following. So here is our tangle. We choose a base point that is to the left, and then every time we go around an edge. So this group element that we assign to an edge is obtained in this way. You take the pre-image of this edge, it will be a segment in a tangle, and then you take the holonomy from point P to P around the segment of the tangle, and that's your group element. And these rules at the double points, they follow immediately from the formations of this contour. So if you take the G contour, G path, you can slide it through the intersection point, and the holonomy is the same. If you take the H path, well, you should first return to the base point P, then you go around, and then you go around again. So as a result, you have this this holonomy. So So the theorem is that such decolorings are in bijection with representation variety with the space of homomorphisms from pi1 to G. So it also gives the description of the character variety. The difference between representation variety and the character variety is that in the character variety you take quotient with respect to G. So so this quotient with respect to G is sort of makes it a bit singular, but we're not going to pay serious attention to this here. So then it turns out that there is a local description of the representation variety. Local in the sense that for this description, you don't need to choose a base point and you don't have to kind of describe assignment of group elements to edges in terms of this global path that goes from the base point through all the other parts of the diagram. So it's really completely local description. But again, this is not a new story, it's an old story. So, so again, this is our tangle with the projection, but now let's look at this projection close. So, for example, if we have an unknown, so we're projecting into, so it's also a tangle. It's a tangle from the empty set to empty set. So it's so if we project it to our green plane, this blue is a diagram of this tangle. But you see, this projection creates some kind of infinite cylinder. And in this infinite cylinder, there is a real tangle somewhere. Everything is oriented. So this tangle separates the cylinder into positive and negative part. So then let's take the surface of this cylinder. So to just pre-image of this circle and diagram. So and let's take a epsilon neighborhood of this cylinder. So so then what we can do is we can trivialize the flat connection inside and outside of the cylinder so that it will be non-trivial only in this epsilon neighborhood of the walls. And the same we can do for more complicated nodes and tangles. If there is an edge in a diagram, we can lift it again. We can create this cylinder which will be sort of half open. And this cylinder will be separated into positive and negative part by the segment, corresponding segment of the real tangle. So if we consider this all these cylinders, so we have a partitioning of our space R2 cross an interval into such cylinders. And every cylinder is separated into negative and positive parts. And we can trivialize our connection inside of each of these cylinders. So, so if we have a flat connection, then by these transformations, we can trivialize it everywhere except for these walls. So, but now let's assume that G is simple and fix Borel subalgebra in G. So, so then every element of the algebra can be decomposed into x plus x minus, such that x plus is in the positive Borel, x minus is in the negative Borel, and the constant part of x plus and x minus are the same. So then I will use the notation G plus minus for corresponding Borel subgroups in G. And let's define this strange subgroup in B plus cross B minus, so-called dual Poisson group. So it's a group of pairs of elements from B plus and B minus, such that the Cartan part of G plus is inverse to the Cartan part of G minus. So then from G star, there is a natural mapping to G. It's G plus G minus goes to G plus G minus inverse. Of course, the opposite mapping doesn't exist. always, but it's a birational correspondence between G star and G. So, so now what we can do by gauge transformations, we can do slightly better than just trivialize A everywhere away from the cylinders. We can trivialize A in such a way that A in an epsilon neighborhood of the positive wall is in G plus. No, not in G plus. Sorry. In the Lie algebra plus. And A on the negative wall is in G minus. So after these gauge transformations, we have so we have a diagram, we have a tangle, we have a diagram. So we have these cylinders. In the negative part of the cylinder, we have a flat connection that's concentrated in an epsilon neighborhood, A minus. In the positive part, we have A plus. And so, because flat connection is trivial everywhere except for these epsilon neighborhoods, if you have a path that goes through the wall in the positive part, the holonomy along this path is just a group element in G plus. If you have a path that's crossing the wall, negative wall, then the holonomy is a group element in G minus. So, because of this, so these are the two paths. One is going through the negative wall, it's in G. The holonomy along the path that goes through the negative wall is in G minus. The holonomy of path that goes through the positive part of the wall is in G plus. And and so we can assign this pair of holonomies to each edge of the diagram. So if we have a flat connection, if we consider it up to gauge transformation, so then we can do this trivialization. All is left is just these group elements that are assigned to the walls. So naturally, if you have a if you have a holonomy A plus along that path, holonomy A minus along the closest path, then if I want to look at the holonomy around this edge, say starting from this point, then I have to take A plus and A minus inverse. And so birationally, this coloring is equivalent to G coloring, to assignment of group elements to every edge. But now, as in the Wirtinger case, this assignment is not arbitrary. It's originally it came from the holonomies for a flat connection. So that's why there are relations. It's very easy to just having this picture in mind and doing similar deformations as for the Wirtinger case. It's easy to see that for the positive crossing, these group elements that are birationally equivalent to pairs of elements from G plus G minus, they should satisfy these relations. And similarly, for negative crossing, they should satisfy the other relation. So again, these are
confused. When you write here, for example, that the positive parts of B and C are the same. There's something funny going on because you have been sliding the positive parts of B and C over the positive parts A and B.
Where is this saying?
I mean, like your relation, for example, B equals A minus inverse C A minus, suggests that the plus parts of B and C are equal.
Parts of B and C. What? No, if you take a low triangular matrix conjugated with upper triangular matrix, you will have just the full matrix. If C belongs to B minus, then B belongs to B minus. But if C is in B plus, then B
No,
is
no,
just.
that's not my complaint. My problem is why do you conjugate by A and not by D?
That's, I mean, I can, no, these are the relations. This is not a description of a mapping from CD to AB.
I still think there's something funny. It's okay. It's okay.
So here is a strong disclaimer. So every formula here could be wrong. The idea is correct. I mean, pluses, minuses, left, right. I can always make a mistake there. So something like this is correct. I hope it's correct.
I mean, there's something of this sort. I'm not
Something of this sort. Even if this is not correct, something of this sort is correct. Yeah. So, okay. So then it's very easy to see that these local colorings are compatible with Redemonster modes. So as a corollary, if you just forget about the origin of these colorings, that they actually came from representation of Y1 from a flat connection in the complement to a tangle, if you will just start with these combinatorial colorings, then because of this theorem, so these local colorings is a structure on tangles because they are compatible with the Redemonster modes. So then basically prove this simple statement that local colorings on a diagram modulo Redemonster moves are in birational correspondence with the representation variety for a tangle in this cylinder. So that gives local description of the representation variety. But then I already mentioned this, that this funny splitting of G into G plus and G minus, so it's actually, it first occurs in classical integrable systems in the theory of Poisson-Lie groups. So there is a natural Poisson structure there hidden. Before I will come to this structure, so as a result of this previous discussion, so we can now color the category of tangles by this G star colorings. So every G here is a pair, G plus, G minus. So everything is very simple, very similar to the category of diagrams, except now the edges are colored by G, and we consider the quotient with respect to the Redemonster moves. So the braiding is given now by this biaxial relations that I described before. Okay, now the Poisson structures. So we will see several Poisson structures. So let's start with the Poisson structure on G star. So it has a natural Poisson-Lie structure in the sense that G star is a Poisson manifold, and it's a group, it's a Lie group, and the multiplication in this Lie group is a Poisson manifold. And this Poisson-Lie structure is known for many years. So first it came up with in integrable systems. So it was described in this way by Dirichlet. So one way to describe it is the following. If you take representations, say finite dimensional representations of G, then if you take the basic functions for this representation, just matrix elements of this representation, they have these Poisson brackets given by the commutators with the evaluation of the R matrix and the tensor product of two representations, and this thing is called classical R matrix. So once you have a symplectic manifold, the very first question is, what are the symplectic leaves? Not symplectic Poisson manifold. What are the symplectic leaves of the Poisson manifold? They are plain like this. So first you map it to G, then you take a conjugacy class in G, and then you take the image of the conjugacy class. That's a symplectic leaf in G star. Again, this is all birational. And it turns out that this mapping is a birational Poisson mapping. So this is the result of Zhu and Weinstein. Somewhere in the early 90s, 91, I think, maybe 93. So we have a secret Poisson structure. So now you see, if I take the colorings, G star colorings of the diagram, if I just restrict it to the upper edges, then I'll have some elements in G star to the end. If I restrict it to lower edges, I'll have some elements in G star to the K. So in other words, I have projection from the space of colorings to both of these spaces, to G star, or in other words, to G star M cross G star to the K. So, and in addition to this, this group G star has a Poisson structure. So the question is, what's the meaning of this Poisson structure and all these topological considerations, and why it's there? So the answer is very simple. It's kind of another form of the Artier-Wood Poisson structure on the upper and lower planes. And so let's look at the, say, one of the planes, either upper or lower plane. So it's R2 minus n points. R2 minus n points, think of this as S2 minus n plus 1 points. One is at infinity. So the phi 1 of R2 minus n points is just a free group generated by n elements by the cycles around these points. So the representation variety in the space of homomorphisms is just G to the n. And then the modular space of flat connections is naturally isomorphic to G to the n mod G. I think it's, I don't know why I wrote it in such a fancy way. It's just G to the n on G. So I'm sure I will be wasting my time now, and everybody knows this Artier-Wood Poisson structure. So let me repeat it anyway. So suppose that we have a trivial G bundle on a surface sigma. Consider the space of connections on this bundle. So oriented, compact, closed sigma. Then on the space of connection, it's an infinite dimensional space. There is a very natural symplectic form. You take the D capital is the Dirac differential on the space of connections. So so this is a two form on the space of connections. A itself is locally one form on sigma, but if you take the Dirac differential of this form, it's like you're subtracting one flat connection from the other, so that's one form. So this dA is naturally G valued one form. So then you take the killing form and you multiply the forms, the wedge through the wedge product. So this is actually two form on sigma. You integrate over sigma. That's your two form on the space of connections. So it's omega 2 on connections G sigma. So then there is a gauge group. In this case of a trivial bundle, it just maps from sigma to G. It acts on connections. the action is Hamiltonian. The moment map from so the Lie algebra for this group is just the maps from sigma to G. So the dual space to this Lie algebra, these are two forms on sigma with coefficients in G. The pairing is just you take the kind of killing form between the elements of G and you integrate zero form times the two form. So the mapping, the moment map is just the following. The connection maps to its curvature. So then the Hamiltonian reduction with respect to this Hamiltonian action of this infinite dimensional group is just you take the pre-image of zero. It's the simplest Hamiltonian reduction relative to zero orbit. You take the pre-image of zero mod G sigma, and by definition, this is the modular space of flat connections on the trivial G1. So it's the same as pi 1 sigma G mod G. So it's a great result. It means, so it's called the Hamiltonian reduction. So one of the actually striking consequences of this, if you didn't know, it's that this space, which pi 1 sigma to G mod G, it has natural symplectic structure. And then there are various descriptions of this symplectic structure. The nice combinatorial description in terms of path functions, graph functions, and sigma is due to Goldman for classical Lie groups. The story for surfaces with boundary is similar. It's just a Poisson variety, and symplectic leaves. There are those homomorphisms from pi 1 to G, for which the conjugacy class of the holonomy around each component of the boundary is fixed. So if n is components of the boundary, then these subspaces are symplectic leaves. But this is all very nice story, but unfortunately, there is no natural Poisson structure on the representation variety before quotiening by G. So that's a bad news. But the good news is that there is some kind of unnatural Poisson structure on this space. So now I'll describe the unnatural Poisson structure that's due to Fock and Rosley, and the natural one that is due to Ati and Bott. So actually, I'm not going to describe it. It's in the paper of Fock and Rosley. It would take another half an hour to describe the structure. So then there is this statement is the following. So it's the claim that there is a birational correspondence between the representation variety and G star to the n. So the representation variety for in our case is G to the n. G star is birationally isomorphic to G, but it's not the same isomorphism. So the isomorphism between these two varieties is given by the following. You take the holonomy around part of the punctures that is in red, and this gives you if you describe these flat connections locally, it gives you this element, and that gives you a birational correspondence between G star to the n and RG. So then you can think of modular space of flat connections now as G star to the n, 1G. So we are getting close to kind of having a full picture of all these flat connections. So now if you have a flat connection in the complement to a tangle, so you have this modular space of flat connections in the complement to a tangle. From this space, there is a natural mapping to both modular spaces for upper and lower plane, and simply the restriction. And we know that upper and lower planes, these modular spaces, they have natural Poisson structure. If we fix conjugacy classes, this will be a natural symplectic structure. So what we have here, just, this is, at the moment, it's just a global picture. So we have these two symplectic varieties, and we have two projections from L curly. This is the modular. This is the subspace in the modular space of flat connections in the complement to a tangle, where we fixed all these conjugacy classes, and we fixed conjugacy classes for each connected component that corresponds to a circle. So then, if we return to local colorings, to G star colorings, so then again we have the symplectic leaves. Now symplectic leaves means something very local. So we fix the conjugacy class for each G plus minus I. For G plus T minus inverse for each of the boundary components of the tangle. So then same with the quotient after quotienting with the modular spaces, and then the claim is the following, that there is a birational correspondence between these two spaces. So we already established the correspondence at the for the boundary spaces. So there is a birational correspondence for the coloring space, and the images of these spaces are Lagrangian submanicals. And this is all birationally isomorphic. So now we have a complete understanding of the Poisson structure for such colorings, and now the representation theory part. How much time do I have? Okay, good. So definitely enough. So I'm not going to give a description of these algebras. They are given by generators and relations. So what's important is that these quantized universal developing algebras, these are families. You can think of them as families of algebras. You can think of the parameter of the family as a formal variable. If you think about the parameter of the family as a formal variable, so then you certainly want to have some kind of integrality condition before you specialize Q to the root of unity. So before specialization, you have to choose an integral form. So you want to choose a form of the algebra UQG, which is actually over this, right? And there are several such forms. In fact, there are many such integral forms, and there are two very distinguished. One is so-called Lucic form with divided power, and the other is the Concini-Kac integral form. So for this picture, for this consideration, we consider the Concini-Kac integral form, and we specialize Q to root of unity. And the remarkable fact for this specialization is that this is a Hopf algebra, which has a central subalgebra generated by Elf powers of generators. And the remarkable fact is that it's a Hopf subalgebra. And this Hopf subalgebra is isomorphic to functions on this Poisson dual group G star. So this center Z0, it's kind of anomalously big center. So if you consider the family UQ, the center is much smaller. There's simply no such center Z0. So usually what happens if you have a family of algebras, if you specialize to a point, then on the center at this point, you have induced Poisson structure which acts by derivations on the whole algebra. So that's exactly what happens here. So this center has a natural Poisson structure that comes from this deformation family. And geometrically, you can think of this algebra as the space of sections of a sheaf of finite dimensional algebras over G star. So I'll denote the fibers by AX, and again, probably many people heard about the quantum groups at roots of unity. Say in Lustig's version, they are never semi-simple. In this version, it turns out that for generic X in G star, and there is a precise description of what it means generic, the fibers are semi-simple. In fact, the dimensions of all irreducible representations are the same. So it's a very interesting structure. So then you might ask, what is an irreducible representation of such creature? So geometrically, it's a vector bundle of irreducible modules over a symplectic leaf in G star, and the fibers should be irreducible modules over the corresponding fibers of UC. So actually, if you restrict this sheaf of algebras to any symplectic leaf, it becomes a vector bundle. So if you take the endomorphisms of this kind of adjoint bundle for this one, it will be some Azumaya algebra. So then for construction of various invariants of limits and tangles, you need some special property, the quasi-triangularity. You need some special elements of A squared, where A is a Hopf algebra, which will give you the breaking. So our Hopf algebra is not quasi-triangular, but it's quasi-triangular sort of in the automorphic sense. So there is an outer automorphism R curly of the tensor square of this algebra, but you also have to allow to divide by elements of the center Z0. So this outer automorphism, it switches the co-multiplication and the opposite co-multiplication, and then it has all the necessary ingredients to construct invariants of tangles. But the difference between this picture and the usual notion of quasi-triangular compulsion, but that was introduced by Dinkel, is the following. This automorphism acts non-trivially on the center, and its action on the center is the pullback of the birational mapping G star to itself, given by this positive intersection, the one that I described earlier. So then I can just repeat what we did with Renat in 2006. So using these ingredients, you can construct invariants of tangles with values in the category of modules over this quantum group. So objects will be. So then there's a standard discussion, kind of long one, but just so you have to fix irreducible representations for each point on the boundary, and then you also have to fix an element over which the corresponding fiber. So the objects are pairs, fiber over some generic G, and then plus minus one, and you have a collection of such things. And that's more or less the meaning of this talk. So this is all result by Kashaev and myself, where we constructed these invariants, but at the time, neither we didn't care about the Poisson structure, although it was there. And then there was lots of papers that followed. By Girku, Turaev, Blanchet, many people. But somehow this very simple fact that the Poisson structure in Poisson groups is kind of very natural from the point of view of what Poisson structure was never, I think, clearly understood. So now the natural conjecture would be the following: that so if you take the limit when the degree of this root of unity goes to infinity, then we get perturbative Chern-Simons invariant. But the one that is like the contributors where it starts with the so it's just really it's a Chern-Simons invariant on the in the sense of perturbation theory, Feynman diagrams, on the background of this given flat connection. So the leading coefficient must be the Chern-Simons value for this connection, and it's the generating function for this. And then there is a natural place for this Chern-Simons value in the Hamiltonian picture, but that's a longer story that I don't want to say here. But it's basically the generating function for this Lagrangian subvariable in these boundary synthetic varieties. So, thank you.